are the opportunities in the area. And this area is very rich with the universities. We have the University of Maryland, we have Johns Hopkins nearby, George Washington, Catholic University. Well, there are about 9 of them, so I don't remember, or 10. So sorry if I did not name something. So
mentioned earlier.
yeah, I didn't. All right, George Mason, University of Virginia, which is a little bit further away, and so yeah. So there are all these great places, and all of them apparently have some astrophysicists and astronomers working, and there are some students there, right? And so this time the meeting is in a little bit different format from the previous one, because the previous one was sort of it was one day only, and it was very intense, and there was only time for students. And this time we are experimenting with a different format. We have 2 days. We try to split the topics a little bit based on extragalactic, galactic, but not quite based on that only. So, and we, because of that, we have time for extra talks, we hope, and then we invited some speakers from Goddard, from Johns Hopkins tomorrow, to give talks on some interesting hard topics in astrophysics. So I hope that will be interesting to you, right? So some logistical issues before we go to actual science is that there is a Wi-Fi network, and I hope you all are able to connect to it. The information is up there or there on the blackboard. The talk duration, so there are 15 minutes actually kind of total with questions. So if you overrun a little bit, it's not a big deal, but try to keep it to maybe 12 minutes plus a couple minutes for questions. And finally, we try, if technology works, which it all, sometimes it does, sometimes it doesn't, but we try to record the talks through this mic. And the slideshow is also being recorded with the goal of actually putting it on the conference website if it works. So I ask you to actually wear this mic so you can clip it somewhere. And you need to clip it pretty close to your mouth, because otherwise it doesn't really work very well. Okay, so let's get started. And the first talk is an invited talk by Eric Switzer from Goddard Space Flight Center, and the talk is about the actually cosmic inflation and CMB polarization and some recent results which we all probably heard of from the news. So welcome, Eric.
Hello?
So the last thing I forgot to say, I'm going to give everyone sort of a 2-minute warning before the time runs out.
Oh, do you have a pointer?
Yes, we have pointers here.
Oh, perfect.
It should be working. If this one doesn't work, the other one works. Okay.
It's a pleasure to speak here today. I'd like to begin with our standard picture of the universe now. And on the right, you see the recent universe, the stars and galaxies that we're familiar with when we look up at the night sky. As you go back further in time, you reach a point where those stars and galaxies must have formed out of the inhomogeneities in the neutral gas of the universe. And if you go back to an even earlier time, the universe was hot enough that that neutral gas was ionized, and so it was opaque. So the CMB was released in this era when the universe shifted from largely ionized to neutral, and almost all the plots will be of this 2D slice of the CMB. And before that, there's posited to be an exponentially rapid epoch of expansion called inflation. And our goal in looking at some aspects of the CMB is to learn more about that era of the universe. the CMB is quite well measured now. On the left, you see inhomogeneities, or anisotropies, rather, of the CMB temperature. And these show fluctuations at a part in 10 to the 5 on top of the 2.7 Kelvin blackbody background. And you can see that in the plus or minus 300 microkelvin color bar. Now, all the plots I'll be showing to summarize these maps are power spectra. And what these show is the RMS fluctuation power on a given angular scale. So for example, 5,000 microkelvin squared variance on 1 degree. Now, the CMB data combined with several other cosmological probes have led to a now standard picture of the universe, which is geometrically flat, which is statistically isotropic and consistent with an initial nearly scale invariant spectrum of Gaussian fluctuations. Now, it could have just been that the universe formed with those parameters, but we'd like to have some explanation of why that might be the case. And inflation is an especially simple way of getting these properties, the flatness and all the properties listed, by adding a single scalar field in its simplest incarnation to your overall theory. So this is gravity, and then a single scalar field and its potential. And that scalar field drives this early exponential period of expansion. So you can think about what we're doing with the CMB as a sort of metric archaeology. We like to learn about the initial conditions of the universe, so the metric at early times as established by inflation. And if you've taken GR, you know that you can write these perturbations as scalars, so just density fluctuations, vectors, which decay away, so we'll ignore those, and tensors. These are gravitational waves that can propagate to us today or influence the CMB along the way. So the picture is that inflation would lay down these perturbations which influence the CMB, which is what we measure, and use to learn about the early universe. Now, most of what I showed you in this previous plot here is the scalar component of the perturbations. So here you see in red just the pure density fluctuations and how they've established this classic CMB pattern. Now, on the very largest scales, it is possible for the tensors, the gravitational waves, to influence the temperature map and its statistics. And you can see that they slightly raise the level of anisotropies on the very largest scales. So on the upper right now, I show how real data can inform the abundance of gravitational waves at the time of the CMB. So the way I'll parameterize this throughout is by R. So that's the ratio of the tensor to scalar power. And here there's an R of 10. So you can see that if R were very large, it would be easy to see with existing data. And in fact, you can see with the data there that they're consistent with no yet detected tensors. So they say that R is less than 0.1 at 95% confidence. So that's a good number to remember when we reach that a bit later. There are a couple other predictions from inflation. So I should say that the fact that this theory can describe these properties of the universe is somewhat of a post-diction. It was made to describe those aspects. But what we like to do is test unique predictions of inflation to see whether it is, in fact, the correct theory of what's happening. And one of those is to measure the tensor, the gravitational waves. And there are a couple of other ones that have already been basically as well tested as they can be. So the fact that it's nearly scale invariant has been well established through the CMB temperature. Gaussianity of the perturbations is again, about as well established as we think it will be. And so that leaves the tensor to scalar ratio as a unique prediction of inflation that we can hope to test. Now, as it turns out with the temperature, like I show on the upper right, we've actually already saturated the measurement. So we measured with temperature alone this R bound as well as we can, and no gravitational waves were detected. So the way you can beat that bound down further and maybe even hope to detect the gravitational waves is to use the CMB polarization. And the idea here is that at the time of the CMB, there are hot and cold patches. So if there's a region of warmer gas above and, say, colder gas to the side, the radiation from those regions will scatter off of an electron in a way that produces a net polarization. And that gives you a vector field of polarization on the sky. And you can decompose a vector field into an electric field-like or E-mode component and a magnetic field-like B-mode component. So this is through the sort of standard electromagnetic Helmholtz decomposition. Now, the reason this is very, very fruitful for tensors is in the symmetry of those two modes. So on the left, you can see the scalars. So scalars are the sort of standard, the already very well-characterized aspect of inflation. And on the right are the tensors that we'd like to learn a lot more about. So you can see that the scalars produce temperature and E modes, but they do not produce B modes on very large angular scales. Whereas the tensors produce temperature, E modes, and B modes on the largest scales. So in principle, what you can do is measure the B mode power spectrum on large angular scales. And if you see something, that's a clear sign of gravitational waves from inflation, if interpreted. So this is where the field stood before the bicep release. You see that the E modes on top were quite well measured by a number of experiments, and they agree with the standard cosmological picture of density perturbations. On the bottom, these are the B mode bounds, and you can see they're just marching down, again, through a number of experiments, but nothing's detected at that point. And here, I'm sure everybody's seen this. This is the bicep release, where they've really just blown all these measurements out of the water and detected B modes. So this is really an amazing feat that the bound, that we've gone from bounds here to a high significance detection. So as a disclaimer, I'm not on the bicep collaboration. And I will be talking more about some of our work at Goddard, but I would like to say more about the results here because they're so exciting. So I'd like to have a few slides about how bicep did its measurement and some of the considerations that you have to take account of in building these sorts of instruments. And some of the key things are where not to look. So unfortunately, we can't just look at the sky and see only CMB. A lot of what you see in these frequencies is in the CMB wavebands is from our own galaxy. So on the top, you see synchrotron emission, and this is falling with frequency. So as you go to higher frequencies, it's dropping off. And then on the bottom, you see dust and its polarization, and it increases with frequency. So there's a nice minimum in foregrounds, around 150 gigahertz, and that turns out to be actually a good frequency to observe the CMB. And then on top of that, you'd like to look in regions where you're far from the galactic plane. So bicep in particular is down here. Another aspect, if you're observing from the ground, is that you want to avoid emission or absorption in the atmosphere. And these come in the form of water and oxygen lines. And it just happens that there's a wide band at 150 gigahertz where you can see through the atmosphere quite well. And we're, in some sense, lucky that both the foregrounds and the atmosphere have a window there. One thing to note is that you can avoid this consideration by going to space or near space, and that's what we do best. So I'll say more about a balloon project toward the end. So this is the bicep instrument, and you might wonder how you observe at 150 gigahertz. Is that a radio telescope? Is that an optical telescope? You can see here that it's a modest size. It doesn't have to be very large just because of the diffraction limit at these wavelengths. the diffraction limit to get the resolution you want at these wavelengths on large scales. Now, if we look at the optics, these will be familiar from an optical instrument. So you have a window and two lenses. Now, each stage gets colder until you reach 250 millikelvin. So these progressively block IR radiation, which would otherwise interfere with your measurement. But otherwise, it looks like an optical instrument. Then the light eventually reaches the focal plane, which is in this red region in the right plot. Now, if you look at the focal plane, this seems more like a radio instrument. So on the right, this is their focal plane with an array of little antennas. And this is like an interferometric array where you can phase them up to get a beam on the sky. So in this case, you're forming a beam in the focal plane. And these carry the signal on in some sense, just like a radio receiver, an electromagnetic signal on these lines, which eventually go out to this little island. And on this island, the signal is dissipated in this meander and heats up an island, and that temperature difference is sensed by a transition edge superconducting detector. So on the upper left, you see the resistance as a function of temperature of that detector. So what happens is that as you move on the sky, the temperature changes, and through the very steep slope at the transition temperature, you're very sensitive to the radiation. Okay, and as you may have heard, there's been quite a bit of discussion about the interpretation of the B modes in the literature and in the public press. And I'd like to start with some initial tensions that people suggested within, say, the first week of looking at the results. And one of them is if you look at the B modes where you expect to see lensing. So this is how the polarization is sheared by all the subsequent structure as it reaches us from the area of the CMB. You see that the points are all a little bit above the expectation. And another way to quantify that is to fit the amplitude of some lensing template. And here's, sorry about the font size, but this axis is its amplitude, and you see that it's a factor of about 2 higher than what people would have expected. And the second thing that people noted right away is that the value of R that these data seem to be consistent with is huge. So something like R of 0.2. And if you remember from the introduction, the existing bound from the temperature anisotropy was less than 0.1 at 95% confidence. So whereas you can see in this case, it's something like greater than 0.1 at 95% confidence. So those two tensions suggested that there might be some contamination or some possibility of contamination in the B mode data set. And additionally, if you look at the E modes, there's some suggestion, again, where the E mode data are a bit above the model, again, suggestive of some contamination. So all this boils down to how you handle the galactic polarized dust emission. And again, we're down in this region where it's very low. If you were to map the whole sky, it would be something like 1,000 times worse. So this is one of the best regions. The original BICEP release did a very careful analysis of existing dust models. And here they've taken the B mode power spectrum of those. And they show that it is, that all of the existing models were well below the reported B mode signal. Now, about a month and a half or 2 months after the release, Mortensen and Seljak published a paper advocating more conservative interpretation of the B mode data. And they made the point that all of these models, while they do span different directions of ideas about dust and its structure, they all assume the same order of magnitude 5% fractional polarization. So this number of 5% comes from Archeops in 2004, and it made its way into several CMB studies. So just really as an order of magnitude to make some progress, but not intended as an accurate figure. So this 5% has influenced all these models except for one. So what Mortensen and Sojak did was take a more statistically conservative approach and say, let's just take a flat prior on the amplitude of the dust, because we really don't know. So this 5% comes from a region near the galactic plane and not in the bicep patch. Whereas what we should say is, in the bicep patch, we really don't know what the polarized dust emission looks like. So the first thing to do is point out that if you give the polarized dust emission sufficient amplitude, that it can actually explain the bicep data. So those are in black, and then the dust with sample variance is in yellow. And then the alternative interpretation of it as inflationary is in the blue dashed line. Another way of phrasing their statement is to find the posterior distribution of the attention to scalar ratio. So if you say there is no dust polarization, then you measure R of 0.2. But once you admit that we really don't know what the dust polarization is, so just call that a flat prior over a sensible range, then you see that there's essentially no additional constraint from the bicep data. And the reason for that is that there's only one frequency band, so you can't separate out the dust from the CMB component. So this was a rather conservative statement that not saying that the data aren't inflationary, but just that you need to be a bit more agnostic about it. So within a few weeks of that, Raphael Flauger and others published a paper which was less conservative, which made the point that we do know more about the dust now from the Planck data release, and in fact it suggests that the dust can fully explain the polarized signal. So this is one of the models that they examined, and in the green band, and you can see that it agrees with so this also includes the known lensing component, and that it agrees with the bicep data. So they made a number of other observations I'd be happy to say more about in questions about cross-correlation and the spectral index using two bands. All right, so I mentioned that a lot of our tests of inflation, such as the near-scale invariance, the Gaussianity, and the tensor to scalar ratio, had already hit some bounds. And now it looks like even this polarization, this B-mode bound, is running into challenges from foregrounds. So how is it that we're actually going to test inflation to understand whether it's the right theory? And I'd like to talk about two experiments that we're participating in at Goddard. So on the left is Piper, and on the right is CLASS. So Piper is led at Goddard, and CLASS is led by Hopkins, and we're doing the detectors. And the idea of these experiments is to measure several different frequencies where you can clearly separate out the synchrotron and the dust component from the CMB B modes. And that way, be able to say better whether these are the cosmological signal or whether you have to sort of beat your way down through contamination. So I work on Piper, and I'd like to say a few more things about our goals there and how we're building Piper. This is a slightly different way of showing the power spectrum without the L+1 factor normalization. And here you see the B-mode data from BICEP. Now, what we'd like to do with Piper is measure essentially the full sky eventually with 4 different frequencies. and in doing so, measure the B modes on very large angular scales. And on these large angular scales, there's a physically independent effect from the influence of gravitational waves on the reionization epoch. So if we were to actually see the B modes on those scales, it would paint a consistent picture of the inflationary gravitational waves. Whereas if we measured something that turns down or has some other structure here, then that could suggest that there's some different contamination at play. So of these, Piper will be observing the upper four bands at 200, 270, 350, and 600 gigahertz. And the way we'll do that is by flying with filters for those bands. And each one of these will be a single flight in the northern and southern hemisphere to eventually cover most of the sky. This is the Piper instrument. It's all in a dewar. So this is a 3,500 liter liquid helium dewar. And when it reaches float, this little eye hatch will open, and the upper atmosphere, which is basically a vacuum, will pump the liquid helium in this volume to reach 1.5 Kelvin. So everything in this region is 1.5 Kelvin. And the light enters and first hits this polarization modulator and then winds its way through to detectors in this submarine, we call it, because a lot of the time it sits in this superfluid helium. You can see that the dewar is not actually that large for a balloon instrument, but in terms of being a dewar, it is very large. In the optical path, the first thing that we hit is the polarization modulator. And one thing that's great about ballooning is that you can get the sensitivity you can get in a few days of ballooning is almost like a few years of ground observation. And the reason for that is that much of the noise in ground observations is due to emission of the atmosphere. So you're looking at, well, there's an analogy with IR telescopes that it's like looking through a telescope made out of fluorescent light bulbs. Something like that here too. So one way to minimize the noise in a balloon situation is not to have any warm windows. So in this case, when that top hatch opens, there's no window between the radiation and the optical path, and then everything below that is 1.5 Kelvin, so even colder than the CMB. And through that, of not having a window, we get a significant gain in the mapping speed. I'll talk about a few pieces of the technology in Piper that I think are very exciting and lead to some of its particular strengths. The first optical element is this variable delay polarization modulator, and what this is a wire grid and a mirror with a variable spacing behind it, and it rotates linear into circular polarization. And by having that at the front of the optics, we modulate any polarization from the sky at 3 hertz. So in the data on our detectors, we can lock into that frequency and pick out the polarization. Our detectors are in some sense similar to BICEP. So we have an array of islands with a TES, and in this case, the light is just absorbed on this large plane. And this array is hybridized to a superconducting quantum interference device multiplexer, and then read out through time domain multiplex electronics. So here you see the transition for these detectors, and again we'll operate somewhere on the transition and so be sensitive to the temperature fluctuations. The last piece of really interesting technology that I'd like to highlight in Piper is how we stay cold, and that's through a continuous adiabatic demagnetization refrigerator, shown on the right. And in a normal refrigerator, you have a working gas or fluid and say a piston, so you interact with the kinetic degrees of freedom in that gas. In this case, we have a crystal and a magnet surrounding it and interact with the spin degrees of freedom in the crystal. So there are no moving parts, and it provides a continuous 0.1 Kelvin on the coldest stage here that interfaces with the plate. So we're very excited to fly this instrument and see what we measure, and in particular look across several bands and at the full sky and see if we can either confirm the BICEP B-mode signal or beat down through additional foregrounds. Overall, it's a very exciting time for the field. I think we're just on the cusp of understanding how to interpret the BICEP data and getting data from actually a range of future experiments like EBEX that we'll hear about next, that will look at several frequencies and different patches of the sky and really help nail down the interpretation. If anyone is interested in being part of this effort, please just send a note, or I'm happy to discuss in questions. Thank you.
I think we have time for one or two brief questions. Anyone? I'll ask something. So when they launched this, WMAP and Planck, why didn't they think about measuring polarization?
So both of them had a polarization component. So WMAP has excellent, if I go, well, I won't go back to they have excellent measurements of the E-modes on very large scales, but not enough sensitivity to comment on the tensor B-modes. Planck was also designed to measure polarization, and in fact, this fall is expected to have a data release with a statement about B-modes. But
do you have some kind of similar technology to that in place on Planck, or it's different completely in terms of measuring polarization?
It's fairly similar. Planck wasn't designed to really go after B-modes. It was mainly a temperature instrument.
So I'm just sort of wondering why it wasn't designed. Because technologically it was challenging, or?
I'm not sure some of it may be historical that the main interest was just measuring the scalar contribution, and having a B-mode would have been kind of a risky cost driver. Yeah. Yeah.
Right. Yeah. We usually have a delay of 20 years between having an idea about launching something and then actually launching something. Okay. Thank you. So let's see. Can I have your mic? You're going to use yours. Yeah.
Is that good?
Yeah, should be okay. Let me switch the. Usually. There was something on the screen actually. Okay, good. So next speaker is Kyle Helson from Brown, and he will tell us about another experiment on CMB measurements.
All right. Thanks, everyone. I'm a graduate student at Brown, and right now I'm through part of the NASA Space Technology Research Fellowship. I'm doing work at Goddard, so that's why I'm able to be here today. So this is just to give you, this is a picture of EBEX from the 2012-2013 Antarctic balloon campaign, just moments after being released from the launch vehicle, Big Boss. And so the work I'm going to be talking about wouldn't be possible without, of course, a large, very talented collaboration of people. We're an international collaboration with collaborators and institutions in Europe and Canada, as well as America. And of course, the work we do isn't possible without various funding sources. Listed here, again, international source of funding. So thankfully, Eric went before me, so I don't have to tell you as much about the theory behind the science that we're doing. So EBEX is a balloon-borne CMB polarimeter designed to measure the polarization, obviously the cosmic microwave background, and foreground galactic dust. So here's a plot of one of these power spectra, and you can see here this is if the B modes are at a certain level, and you have a contribution from lensing and gravitational waves in E mode signal. And this is again this L+1 and CL. And so EBEX is an off-axis Michiguzi Dragone type telescope with a 1.4 meter primary mirror. We use approximately 1,400 of these transition edge sensing superconducting bolometers at 3 different frequency bands with 150, 250, and 410 gigahertz. Our bolometers are feed horn coupled, so we get 8 arc minute resolution in all 3 frequency bands. And in a similar method to what Eric talked about, Piper, we use a sapphire half wave plate to modulate the polarization on our instrument, and then a fixed wire grid. And so here is a kind of an actual picture of the instrument, and then a 3D CAD model. And so here, this is moments before launch, hanging off the launch vehicle. From the bottom of these solar panels, the top is about 26 feet. EBEX weighed in right around at the NASA mandated weight limit of 6,000 pounds. And you can see these large sun shields and then the baffling around the primary mirror. And these panels are actually radiating panels that we use to cool the electronics that we use to read out the detectors. And so as we kind of undress the experiment a little bit, you take off the sun shields and the baffling. You see this is our primary mirror. This is our secondary mirror. And then this is the window into our receiver, which is this blue cryostat right here. And you can kind of see sticking out. And then we have a lot of various pointing sensors and things like that on EBEX. And these 2 red kind of cylinders are star cameras. These green boxes are the gyroscopes. And so within the cryostat here, so after kind of this level, everything inside here is at 3K or below, or 4K, I guess. So we have the half wave plate that sits here, and so we have the incoming light polarization is continuously modulated by this half wave plate. With these lenses, this polarizing grid here splits the orthogonal polarizations Q and U to separate focal planes, which lets you read both polarizations simultaneously. And then our focal planes are cooled with a helium-10 fridge. And then we have squid electronic readout boards. And so here's a close-up view of the cold optics. See here, this is the fridge. You can see the 2 focal points here and here. And this is a cold stop. And so everything within here, like I said, is, it says 1K, 4K down here, and then our focal points are kept at 250 millikelvin or so. And so a little bit more about our detectors and polarimetry. So this is a picture of the half-wave plate. It's supported on a superconducting magnetic bearing. And so it has a warm drive motor that sits outside the cryostat and a drive shaft that runs all the way down to drive this Kevlar belt that actually you kind of see here. And so then the wave plate is suspended on a superconducting magnetic bearing and then spun up to about 1.23 hertz. And this frequency of about 1.25 hertz sends our polarization modulation signal up to about 5 hertz. And so within our data, we look at this 5 hertz band for our polarization. Here's a picture of the focal planes, and you can see that, so to get 3 frequency bands, you have to be smart about where you place the detectors, and so you have to put generally put the higher frequency detectors in the center of the focal plane, and then you have the lower frequency detectors on the outside. And so we have more 150s than 250s, and then 410s. And this ring is a is the diameter of our cold stop, so all the detectors that lie outside that ring are dark detectors. And we have 2 of these focal planes, and they're each to measure the separate orthogonal polarization components. And then to read out these detectors, we use a 16x digital frequency domain multiplexing system that was developed by the collaborators at McGill and is used on several other CMB experiments like the South Pole Telescope and Polar Bear. So our 2012 Antarctic campaign, we launched on our first science flight. We had an engineering flight in 2009 from Fort Sumner, New Mexico. And so we were able to take 11 days of science observations, which is this kind of bolded track that you see here. And then to facilitate easier recovery, the payload was allowed to continue around the rest of the continent. It makes it a lot easier if you can recover the experiment not too far from where you launched it. The reason that we only took 11 days of science observations is because that's how long our helium bath lasts. And so once we run out of liquid helium, then we warm up to nitrogen temperature, and so we can't observe with our detectors. We floated approximately 35 kilometers, which is 105,000 feet. We recovered the hard drives and some of the computers in February of 2013, and then we didn't recover the rest of the payload until October because of weather. And so when you're in Antarctica and the weather gets pretty harsh when the springtime comes around. So we took we measured approximately 6,000 square degrees of sky, and looking at the sky, we used RCW38, which is an extended star cluster, as a source of on-sky calibration, as well as taking passes over the galactic plane, which is a strong polarized source. And then we'd also take periodic dips in elevation while we were observing to measure the loading due to atmospheric depth. So if you're looking above the atmosphere, if you dip a little bit lower, obviously you get more atmospheric column. And so now we're churning through data analysis, and one of the unique challenges to ballooning is that during flight, you don't have the extremely accurate pointing that you have on the ground. And so we employ a handful of other pointing sensors that let us reconstruct our pointing to very high accuracy and precision post-flight. And so in flight, we have about 1 or half degree accuracy of pointing, in post-flight, where our aim is to look at approximately 10 or 11 arc seconds in pointing. And so the pointing is actually facilitated by gyroscopes and star cameras. And so at the end of every telescope throw, you take a picture of where you're observing on the sky. And then to integrate, and using the star patterns that you see, you can calculate exactly what direction you're pointing. And then to integrate the pointing in between those two images, you have gyroscopes. And there are several different algorithms and methods for looking at this gyroscope data, which is why you get this kind of spread over large uncertainty range. One of the other challenges, of course, is calibration. And so luckily, the temperature of the CMB is known to many significant figures, so you can calibrate your absolute temperature to Planck and WMAP data. As here, if you can see, this is a 250 gigahertz bolometer, and you can see this is the best fit line, and this is several EBEX signal counts, detector counts versus Planck sky signal. And also, like I said, RCW38 is nice because RCW38 is about 6 arc minutes in diameter, and so with our 8 arc minute beam, it looks pretty close to being a point source, and so we can use this as a polarized calibration. So here's some preliminary data that we have. This is of a galaxy crossing, and a galaxy crossing is a strong polarized signal, so it gives a nice bright signal in our instrument, and it's a good first sort of map. And so here you can see just total temperature from the galaxy, and then here's the polarization power that we're getting from the galaxy. And this is from about 20 minutes of data with about 100 detectors. And so moving on into the future, we've put in a proposal this past spring to do a second round of EVEX, and we've called this one EVEX 6K, and it's because we are upgrading to 6,000 detectors. And what we want to do is use this new type of bolometer that they're called sinuous antenna multichroic pixels. And so what it lets you do is have up to 3 frequency bands per pixel here on one of these wafers. And so that would let us get up to, say, 4 different frequency bands, and because each of these detectors can detect both orthogonal polarizations at the same time, we can do away with having that wire grid to split the polarizations. We can just have a single focal plane, which will do things like improve hold time. And then you can see here, again, we go with the scheme with having the higher frequency in the middle, and these 280 gigahertz bolometers would be only single color. And so for EVEX 6K, of course, the big talk is what's going to kind of look at this bicep result. What's sensitive, or future experiments will hopefully be sensitive enough to have something to say about bicep. And so EVEX 6K is one of those instruments. And so if we do see, if R does equal 0.2 in reality, then EVEX 6K will have about 2.5 times more precise measurement than the current determination. And if R is less than 0.2, as many people have been said, then we have sensitivity, or 2 sigma sensitivity down to R of 0.008. And so you can kind of see this is a R of 0.2 here, and these are, and then R of 0.03 here. Okay. Sorry. So summary. EVEX is a CMB polarization experiment that flew for the Antarctic flight of 2012 and 2013. We observed 6,000 square degrees of sky. We have these large arrays of these TES bolometers, and we're currently going through data analysis, and we've also put in a proposal to do EVEX 6K, which is a future generation CMB balloon experiment.
Okay, thanks, Kyle. Couple minutes for questions. All questions? Then I'll have to.
Yeah. So for CMB, we don't necessarily need down to like single arc second pointing. Yeah. The state, pretty much the state of the art right now in CMB balloons is still using star cameras and gyroscopes. So this method is definitely the kind of as good as it gets for balloons. In flight, it's really hard to have a feedback system where you'd be calculating more accurate pointing solutions and then having those feedback real time into pointing that you're actively scanning. So it's much easier just to rely on sort of coarse pointing sensors in flight and then reconstruct it later. And as long as some of the pointing sensors work during the flight, you don't have that much of a problem. And even past experiments like Boomerang flew with zero pointing. None of their pointing sensors worked their whole flight in like '97, I think, and they managed to get a Nature paper out of that. So.
Yeah. You seem to be very knowledgeable about all stuff you're talking about. So you're working on this for a few years?
I just finished my 4th year.
Fourth year. So did you actually get to go to the Antarctic?
Yeah, I was there for 2 months. So.
Isn't that cool?
Yeah, so yeah, I guess it's one of the two premier destinations, right? You have Chile or Antarctica, kind of for.
So one more question. So are these things? So Eric mentioned a couple experiments.
Mm-hmm.
You have this experiment. There is this bicep. Are they all competing head-on, or they're complementary, or what?
Kind of both, right? So everyone wants to be first.
Yeah, but
obviously, but at a certain point, I think, people, especially I think in ballooning, we're happy to share kind of different techniques and talk about things that worked, didn't work. We actually, because my lab was actually a part of the BLAST experiment as well, and BLAST has a lot of people at Toronto, and Toronto has a lot of people who work on Spider. And so, and Spider's a competing ballooning experiment. So the ballooning community is fairly small.
Okay.
I don't
so
think
there's a lot of things going on in this area, as you can see.
Yeah.
Could you put up that slide where you showed the plane crossing and then you showed the polarization?
Yeah.
Yeah. So was this sort of a calibration sort of purposes, or is that your real data produced without polarization?
So this what we were looking at right now is we know that the galactic plane is a strong polarized signal. So as we're going through a first round, we want to make sure that we can calibrate on the galaxy for polarization as opposed to.
So that's basically what this is about.
Mhm.
This portion.
Yeah. So I mean, this isn't going to be any
Yeah,
sort of
that's what
science data. It could potentially be more interesting since we have higher frequency data for part of the bicep patch. So that's something we can also look for. And like even Spider, when they're supposed to fly next year, they only have frequency information up to 220, and they might not even fly their 220 gigahertz wafers. They have 90 and 150, and so it's kind of like right now it's Planck, where everyone's waiting for Planck because Planck has lots of frequency bands above 150. But
All right. Thanks. All right. So the next speaker we have is Jordan Aguirre. Is that? Okay. Sorry. Yeah. You can. Yeah. And he comes to us from the Catholic, right, University, and we're gonna make a dramatic jump from the cosmological scales to something which is very nearby, and that is our sun, right?
Yep.
Yep. Right. So let me close to your mouth.
Okay. Yeah. Seems like you can hear. There's a function.
Function 4. Just wait. It takes some time.
30 degrees. Okay. Mm. It is.
Sorry.
That's fine. Is it? It's kind of offset, but hi. So I'm kind of used to at this point being the only one who, talks about the sun in Astro conference, but it's fine. So I wonder. I bet you guys wonder, what HMI and AIA data is. It's just these are just two instruments on the Solar Dynamic Observatory NASA satellite. And in few words, HMI just measured magnetic field on the surface, and AIA measured high energy emissions on the corona. And in a nutshell, what we want to develop here, it's a very simple method to analyze the correlation between these two data sets. I mean, the same satellite is looking at the sun, and we can actually have co-align. I mean, we can actually, look at the same spot at two different, heights. So we want to see how they correlate to each other. This is more or less how it's, going. I have to say this is like the second part of what will be my dissertation. So it's just starting. So the results are very preliminary, but we basically have two main reasons why we want to do this. First of all, it's more or less well known that the solar corona and the photosphere exist, or there is a dynamical coupling between these two. And in particular, we want to know how this coupling, physically works, and also how this coupling might actually give you some information about the solar explosions that actually give us, and also because especially because we can measure magnetic fields on the surface but not in the corona, so we can rely more on the measurements on the surface. And the second part is the second reason is a little bit more practical. The truth is like what do we want? What we want to is improve the way that we forecast this type of a solar explosion or explosive event, right? So I'm going to show more or less what type of analysis we're, how we calculate these correlations and other quantities that we can calculate from the calculated correlations, the preliminary result, of course. So it's very well known to a certain point that the photosphere drives the phenomena in the corona by a process that basically is based on the emergence of flux. We have the magnetic field under the surface of the sun, and it's being twisted and shared around by turbulent motions. At some point, the magnetic field just pops out, breaks through the surface and form very complex patterns in the surface that basically produce what we call the active regions. The active regions, we'll see it in this video. It's just a different way to see what we see in white light as the sunspots. So we see here, this is in the surface. This is magnetic field in the surface. Red is positive polarity. No, blue is positive polarity. Red is negative. And we see as this magnetic field rises, we can see how in the corona, we have enhanced emission. The very bright and sullen spots in here are basically flares. They are different type of flare, and they are normally classified based on the peak of the energy that can be measured in X-ray, basically. So it is when we want to. So the truth is like only in active regions or in regions where the magnetic field is really strong, you can see activity like this. But the problem is not really clear how you translate the emergence of flux in this image to this one, because it's just not a correspondence one-to-one. In the quiet zone is a part of the sun when we don't have active region. It's quiet in the sense that there's no strong magnetic field, but there's also a lot happening. If we see this plot here from these people, basically they try to what they try to do is like, okay, more or less the same. If we if we put on top of each other the coronal data, which are like the black dots, no, on the other way around, it's the color plot, and then we overpose some magnetic field data, how they correspond to each other. And they calculated the fractal dimension of this image that we have here for each one and the cross correlation. I'm not going to get much into detail of this plot, but basically what it says, the fact that in space and time, there is some level of correlation between these two set of data, at least in the quiet zone. We did some work last year on trying to explore, what happened when we're trying to apply certain statistical analysis to active region data. And we actually found the fact that in active regions, the power spectral density do follow power laws, and that it's very important actually to characterize photospheric magnetic data in space and time. Even if we see very complex patterns in space, it's not just the pattern; it's also how they evolve in time. So any explanation on how the magnetic field in the surface might evolve and might evolve towards to produce some explosive event might actually, it has to take into account analysis in space and time, which is something that it hasn't been very explored recently. On the other hand, why we wanted to have an idea of, or why we want to do these on the other hand, is because what we call the space weather The space weather is just the conditions of the plasma around this, the Earth, and how this actually affects our day-to-day, especially on the technology. I'm not going to go into details with this plot, but there are several ways that the space weather and this solar explosion affect us. And in particular, we aim to hopefully, we aim to, like, if we can understand the correlation between the two quantities, hopefully one of, we might be able to calculate some quantity that will give us information of when an active region is probably, developing or just evolving towards producing, this type of flares, especially flares. I'm concentrating more on flares. Okay, so quickly, the active regions that there's the data that are going to be shown, here which correspond to the video. So correspond to this active region. This active region is from 2011, and this is the satellite SDO. This active region actually produced a couple of major flares, an X-class flare, a couple of M-class flare, which are the ones that we're focused on, are the ones that we want to predict, eventually. And the data set that we use is the HMI, or line of sight magnetogram, which is a magnetic field, and the coronal emission maps from the instrument AIA, in particular in these two wavelengths. If we see here, AIA actually measures 7 wavelengths, which each one has or correspond to a different peak temperature. So basically, analyzing different wavelengths is basically analyzing different part of the plasma, which is at different temperature. All right. So in one sentence, what we're going to be measuring is the correlation coefficient. Now, how are we going to measure it? So we have this definition. We're going to have two quantities. We might either calculate the autocorrelation, which corresponds to this case, in which B is the unsigned magnetic field, or I is the intensity of the coronal emission. And but in particular, we also want to keep some time dependence information in it. So what we do is, if we take the data cube that we have a stack of these images like this, and we're going to shift it in each direction, but also in the temporal direction. But then we're going to do some cutout defined by the maximum of the shifts that we have, so we can keep the statistics or whenever we calculate the correlation coefficient, it has to be with the same number of points. And the same thing we do in time, and we define the shift in some power scale, so we can see, we can see basically different scales of the of shifts. All right, but when we do this quantity that we have here is a three-dimensional quantity. It depends on these three variables that we have here, the 3 shifts, the space and time. And in particular, we know that the coronal, this is all HMI data. In particular, the photospheric data has a preference in the direction of the solar rotation. So if we, see, for instance, in this direction, it's going to be, quite different if we see it in this direction. So what we decide is just to consider the isotropic case. We just integrate over circles in this image, and we obtain a plot like this. And we see that each one of these, at each different delta t, we just have a decay in this way. However, this is still a lot of information, so we need to somehow arrive to one single quantity that we can just see the evolution in time. It's really hard to see this plot here, but from the plot, the decay plots that we had before, what we do is we will measure the E-folding decay in this case. It's just the maximum value what we have over the value of E. And in this case, in the case of delta T, and in delta R, which is the the quantity I define, just basically the radius of circles, and we see how they behave completely different. In this case, in these plots, these vertical lines here just represent a time when during the active region evolution the X-class flare happened. So what we were interested in see, well, this thing might evolve in such a way that some signatures might be seen here before the flare happens. In this case, I mean, we see a very clear growth towards a period that might, be sort of, constant or not. We're still analyzing this data. But in this case, for the e-folding times, it's much more difficult because it seems like in time, the HMI data decay much slower, so we have to use some fits here. And it seems just like the fits are not really working very well because this part is just really noisy, only really close to the center of the images. Maybe we can, have a smooth data. And if we try this same, technique with the AIA data, we actually see, different responses. Actually, we actually see that there is a little bit more of structure, but the AIA, we are still analyzing the AIA data. Before the last step, or we're just trying to define different quantities that we can calculate from the correlation coefficient. And one of them is like, well, let's try to actually put all together in one single function and calculate some parameters that characterize a single function. So if we do the same procedure of combining the spatial and temporal evolution, we have to, the spatial and temporal scales, we have to assume some characteristic velocity. In the photosphere, in this case, we have either the MHD, a characteristic velocity, it's a velocity in which you'll say two parts of the photosphere might interact with or might just share some sort of information by. So we have in the first case we have the horizontal convection, so basically how the plasma moves in the horizontal plane, and then you have some sort of MHD wave interaction. In that case, we see a not very clear decay here, because actually for very early times we see that sort of decay like a drop, and then it seems like a very more smooth, possibly exponential decay here, and then we construct these plots here. But this is we're just trying this technique. The total evolution is actually 240 minutes, so we don't have the whole evolution yet. We're still calculating these numbers because it takes a long time. And eventually, this what we want to do is once we characterize the outer correlations of each set of data, we have to move on into a cross correlation. We did some preliminary tests, but the shapes of these correlations on surface are kind of strange. So what we found out so far is the HMI data actually display very long correlation times. We believe that's related to the lifetimes of magnetic elements. Like if you have a sunspot there, a sunspot can actually live for days, and we believe that's why it's making the HMI data to display correlate like decays that are actually go longer than the temporal shifts that we use. Well, the AIA decays, data decays pretty fast, and we believe because the explosive events, even if they are small, they are just very transient. So this is completely ongoing, and we're just trying to use this technique. So the same. In this data, but especially we want to, analyze several wavelengths because we will be, looking at different temperatures of the plasma. All right. Thank you. According to mine, I went like over a minute.
Yeah, that kind of research actually, I don't know why there are so few talks on solar research at this meeting, because you can argue that that kind of research has some impact on the Earth, right? Because of that space weather, the cellular, the satellites may be affected, the cellular network may be affected, and stuff like that. So you can actually explain your grandma, why, she pays taxes and what for, right? Unlike, the cosmic background polarization. How does it affect us, right? Okay. Do you have any questions? No? Anyone? So I have a question. I would naively think that this activity is related to how much you twist the magnetic field, right, in the sun. Mm-hmm. So you have this instrument which measures the structure of the magnetic field, right, on the Solar Dynamic Observatory.
Yeah, mostly
or just
the magnetic field on the surface.
Yeah.
Yes.
Okay, so you can see that it evolves, right, with time. So can you actually see some kind of twist developing and then it's followed by some flares? Can you just predict the flare based on how the magnetic field changes?
The problem is like in the surface, I mean, with the way this data can only measure magnetic field on the surface. Mm-hmm. The magnetic field is actually a full 3D, sort of arcade structure. But the thing is, in the corona is a very thin plasma, so there's not enough photons there to actually measure the magnetic field. So there are models that reconstruct the structure from this type of information, and then you can use that, and we do use that for some forecasting purposes. But
okay, thank you.
You're welcome.
If there are no questions, then I'll do. Then the next one is Nicholas from, let's see, University of Virginia, right? And Nicholas will be talking about the measuring stellar parameters and abundances, I suppose, in the main sequence stars, or?
Well, it's about binary stars.
Binary
stars,
right. So, okay, so your talk is on this. So, right. Can connect it to that usual one.
Yeah, but it just killed my internet, so can I use the Mac instead? Oh, okay. Is it on the Mac?
Yeah. Okay. So you want to go to internet?
Yeah.
This one?
Yeah.
Oh, sorry. That's a need to. Sorry about that. Just slight delay.
It's a fourth-dimensional object there.
And whenever there is a delay, feel free to use the, the coffee stand.
Get some coffee.
Yeah, it will pick it up. See, and then you. So how
You
is
just
it?
press it. Maybe. Wait, hold on.
You have to drag it
Drag it
to
up.
the other screen. Let me
Oh yeah, drag.
Let's see. I can do it here. No.
Alright, that looks like it works. Alright, hi, sorry about the delay. So, as they said, I'm Nick Troop, I'm from UVA, and today I will be talking about the Apogee survey and how we can use it to study binary stars and different galactic environments and different stellar properties. This work was done in conjunction with two other graduate students at the University of Virginia, as a sort of, came stemmed off of a final project from a class, and we've been running with it since. So first, I'm going to sort of introduce the Apogee project for those who aren't familiar with it and how we can use it to study binary stars. Give a quick review of binary star formation and current state of observations of binary stars. Talk about how we selected and sorted our sample. Talk about our discussion, talk about our results and discussion, and how we're going to follow up what we did for future efforts. So my advisor actually wouldn't let me come here unless I put a shameless plug for his survey, so here it is. The Apache Point Galactic Evolution Experiment is a slow digital sky survey. Survey was selected and it's ran for about 2 years now. It is here and it just finished the second year's observation. It's got renewed for 6 more years of observations as an SDSS-4 survey, and hopefully, pending funding, it'll be continued on into the southern hemisphere at Las Campanas Observatory. So it is a study of a wide range of galactic environments. The primary goal is to give a full chemical and kinematical picture of the galaxy. And it does that by using a high-resolution spectrograph in the near-infrared. It uses the near-infrared so it can punch through the center of the galaxy, see through all the dust and gas there, to see through the other side of the galaxy. Thanks to hard-working pipeline developers, the spectrograph is able to achieve less than 100 meter per second RV precision, which is much lower than what the initial survey was expected. And also, in development is the Apogee Stellar Parameter and Chemical Abundances Pipeline, which will automatically take the spectra and spit out stellar parameters and abundances of 15 elements. So, why are we using a galactic evolution, a galactic structure experiment to study binaries? Well, to achieve a good solution for stellar abundances and parameters, you need to get high resolution spectra. So the typical number is 100, signal is 100. In order to do that, you have to re-observe these different plates multiple times because of this fixed nature of the Sloan observations. You get an hour and that's it. And then your plate gets taken away, and then so you have to put it back in later, and so you have to re-observe it multiple times. That's fortunate for us because that means we have basically a bunch of stars that have a bunch of RV measurements over different epochs and at different times. So and in order to combine the spectra, so you have to get an RV solution for every single visit, every time you observe. And Apogee is super efficient. It can observe up to 300 targets for every observation, which means it has added up to a large sample over 2 years, over 100,000 stars. And because it's a galactic evolution experiment, it has surveyed a large range of galactic environments and stellar populations. So you combine the multiple RV measurements with the chemical abundances, you get a unique study of stellar multiplicity that really hasn't been fully explored before. So a quick review of what we know about stellar multiplicity. Current observations have found that at least 50% of systems have at least 2 stars. So that means binary stars are common and happen everywhere. The current leading scenario for binary stars is this idea of disk fragmentation. A lot of work is still theoretical work is being done with that. A lot of it doing with magnetic fields, because when you don't know what's going on, you invoke a magnetic field, right? So we also have a fairly good picture of how planets are formed. Planets are formed by this idea of core accretion. You get a rocky core, dump gas on it, you get a gas giant planet. The gray area is really how are brown dwarf companions formed. We've found a bunch of brown dwarf companions orbiting solar mass stars. How are they formed more like binary stars, like failed stellar mass binary stars, or are they formed like runaway giant planets? It's sort of a little bit of a gray area. And of course, not all binary stars survive. A 3-body scattering interaction can destroy a binary system, and a lot of that happens in stellar clusters where it's really dense stellar environments. So, as with any survey, we can't use all the data. Not all of it is quality and good to use for what we need to do. So we took the first 2 years of Apogee observations, about 100,000 stars, and we first selected things based on the quality of their velocity measurements. So first things first, we have to get rid of anything that has less than 3 visits, because If you don't have 3 visits, how can you tell if something is RV variable? It's kind of no point. We wanted things that had at least signal noise of 10 for each observation, because you need good lines. You don't want a lot of noise, or the RV measurement will go out the window. We wanted to get rid of stars that were flagged as rapid rotators that had really broad lines, because that can also mess up your RV measurements. And also, some things just spit out ridiculously high velocities, so those just got thrown out. So for most things, we used just this selection, the velocity selection, but when we wanted to dig deeper and investigate stellar parameters, we had to select based on the quality of those parameters. So first things first, we needed to, if the pipeline did not converge to a solution for the parameters, is no good to us, so we can't use that. We went with the bare minimum signal noise, 50, and we wanted good fits, good spectral fits away from the edge of the grid of spectral grids. And we also want things that were within a calibration range that was used to make sure the data were good. Okay, so we had to do a little bit of tweaking to get the velocity scatter to represent something physical. What this pipeline spits out is this standard deviation of scatter about the mean velocity. But typically, when you talk about companions, you do this thing called an RV semi-amplitude, and it has a lot to do with the mass ratio, and inclination eccentricity, and the period. So in order to do that, we came up with sort of this rough by eye fit correction to translate a scatter, a standard deviation to a range. The other thing we had to consider is how well sampled the true RV curve is. Unfortunately, you can't have a perfect, complete sampling of the binary curve, but we came up with this idea that the sampling is based off, how well sampled something is based off the period and the number of visits. But this turned out to be a lot more difficult to characterize than we initially thought. So for now, we just keep in mind that what this observed velocity range scatter is a lower limit of the true velocity scatter. All right, so now we have come to the point where we can sort our sample based on this velocity scatter. So first things first, we need to consider what makes a single star. So to do that, we basically made a histogram of all the complete samples RV scatter and found this peak right around 100 meters per second as expected, and basically force fit by eye fit a Gaussian to the left side. This long tail is all likely binaries. So we considered anything that had less than 0.2 kilometers per second to be a single star. And anything greater than 0.2 kilometers per second is likely some kind of binary. So we also had to consider the error of the individual RV measurements. So the sigma is the individual measurement errors of the RV measurements, and anything that had anything where the 3 times the error didn't match up the RV variation, we can't statistically say that that's definitely a binary, because the measurement errors could easily throw that into the single star category, so we just threw those out. Anything that had greater than this 3 sigma detection, we kept. And we did something similar for the single stars, where if you add up the variation and the error and it is above 0.2 kilometers per second, you're getting into the regime where the error might push you into the binary star category. So we threw those out as well. And everything else that remained we labeled as a single star. Same thing. So we did some calculations and found that anything that was above a 1 kilometer per second RV scatter, we consider these things called stellar mass binaries. They're things that are at least 0.1 solar mass or above. Anything below 1 kilometer per second is what we call these brown dwarf nominee binaries, things that are likely to have very low mass companions. However, this category is pretty solid because, as you guys mentioned before, this K is a lower limit. So anything in this category is most likely actually stellar mass companion or greater. These categories are a little fuzzy, but because something that has a very long period or high inclination could bump something into the next category. But we just keep in mind that these things are lower limits. So finally, we're able to spit out a binary fraction. We find that sort of a global binary fraction of 0.61, which agrees fairly well with what's been observed, about half. We find that, interestingly, that likely lower mass companions are more common than equal mass companions. Something interesting happens when we choose between things that are just selected by RV quality standards versus parameter quality standards. This equal mass binary fraction goes down by a tenth. So why we think that's happening is because if we recall the parameter quality criterion, if something doesn't converge, the way the parameter pipeline works is that you have basically a big old library of stellar spectra. If it doesn't match well, it doesn't know what it's doing. So we think these are all double-line binaries because it can't find a good thing to match. All right. So now we're on to what we see as parameter, these trends with parameters. So this is sort of the first thing we saw. We saw that as you go to more metal-poor stars, systems, the binary fraction goes up. So and we think that this is some kind of relic of the formation process of binaries. A recent paper, a theoretical work, has shown that more metal-poor protostellar disks are more likely to fragment. So that agrees sort of with what we're seeing here. And you can see we bend up. Go back. So we bend up the metallicity, and we see that the peak of binaries is actually, is indeed slightly more metal poor than the peak for single stars, which is about here. So we also took just the abundances of alpha elements. Alpha process elements are things like silicon, oxygen, anything that's multiple of 4. And we find that these low mass binaries, the fraction of those start to go up as you go to more systems more enriched in alpha elements. So this may be an indication that these brown dwarfs form very low mass companions might actually form more like planets, because a paper by Robinson in 2006 found that systems that are enhanced with alpha elements are more likely to host planets, or giant planets. So this is sort of the same trend we're seeing here. So that may be the case that what we're seeing here. So while the abundances can tell us about what the formation of the system, the trends with surface gravity and effective temperature can tell us about how binary systems evolve, possibly. So if you think of something that's more inflated, as a star gets more inflated, its surface gravity will go down, so we see that there's sort of a trend downward here. So that means maybe that as a star inflates, its companion either gets destroyed, scattered, or pushed out beyond our detection limit to a longer period. There's a very curious spike up here that I am kind of confused about, and I want to investigate further. It may be due to low number statistics, but it's very interesting that these very low gravity things have a spike up in binary fraction. And we see a very similar thing with effective temperature. Cooler stars are going to be more inflated. Hotter stars are generally going to be more compact for this type of stars we're dealing with. So we decided we wanted to take a look see if the distribution of binary fraction through the galaxy is significantly different. We really didn't see much of a trend at all. We did find these interesting packets of fields that have binary fractions close to 100%. So, and we thought, oh, they're compact, they're in the halo by themselves, these are probably globular clusters. So we decided we want to see how binary fraction gets changed between the field and clusters. So when we split it up, we picked field stars or anything that was not in a dedicated cluster field. We found that the binary fraction is slightly lower than the global. And then when we considered cluster stars, things that luckily the targeting people for Apogee selected things that were cluster members for us, so we were able to use those, and found a fairly significantly higher binary fraction for clusters, which we've I thought was kind of odd because if you think of a cluster should scatter binary stars, not necessarily make more of them. So when we split it up into, oh my gosh, go back. Hold on. Oh, for goodness sakes. Oh no. I broke it. Yeah.
Left? No.
Left?
Let's see. Where is your...
It's a...
Can you... Is it your
Yeah, that's it.
You have to scroll through it.
Yeah, I can do it.
Should I push the...
Yeah, make that a minute. Maximize that or hit the present button. I can just go through it. It's fine. Yeah. I'm just having the worst luck. I'm sorry, guys. Okay. All right, so like I said, we split up the clusters into open clusters and globular clusters and found these open clusters have a much smaller binary fraction. I did it again. Why doesn't it like me? Maybe I'll just use the computer from now on.
Yeah. Where did it go? Let's see.
There you
Is
go.
that
Yeah, that's it.
slide?
Yeah, I'm not going to touch this.
Switch it like this.
I'm going to stop messing with that. All right, so open clusters had a lower fraction of binaries versus globular clusters, and this is probably remnant of the metallicity trend we saw before. And more or less, we saw that more metal poor clusters had a higher binary fraction than more metal rich clusters. So that's probably the primary driver of that. All right. So to summarize, we came up with this quick selection method for binary stars. In particular, we have a way of picking out double-line binaries from possible double-line binaries from the Apogee dataset. We found a global binary fraction of about 0.6, which is in rough agreement with what has been observed so far, and that low-mass companions are more common in the galaxy. We see these trends with these stellar parameters. We think that the metallicity and alpha abundance trends have to do with the formation of binary systems, and that the effective temperature and log G trends may have to do with the evolution of binary systems. No major trends were seen as you look in different galactic latitude and longitude. And when we looked at clusters, binary fraction, we confirmed our metallicity trend. And for all of efforts, this would be really an easy thing to just incorporate into the pipeline for Apogee to flag binaries. We would like to investigate these potential double-line binaries, apply these binary disentanglement routines, which allows you to split the two component spectra apart, and we can run abundance analysis on those. We'd like to be able to run Keplerian orbit fitting on all these stars, which may require additional observations, and possibly investigate binarity trends with detailed abundances. Yeah, thank you for trudging through that with me. Sorry.
A very interesting talk, despite
Yes.
annoying technical issues. Yeah. So, any questions? Quick.
Yes.
All right. So radial velocity or the semi-amplitude of radial velocity is a very powerful method. So you were saying for your future work, you're going to do some double line binaries. You can look at different elements such as orbital liberation as well as the masses of those two components as well.
Well, we can talk. That would be a very interesting topic, and that's what the sort of Keplerian orbit fitting. In order to get the masses and mass ratios, you need to actually do that orbit fitting. We can't get that straight. We can't get a definite answer for that just from looking at the velocity scatter. You actually have to go through and do the full orbit fitting. Yeah. So that's definitely something we want to move forward and do.
Another quick question.
Yeah.
Do you find any strange objects? Like, I'm actually working on neutron stars, black holes. Do you find something moving very quickly, or maybe something around a neutron star?
Well, I mean, there are things that have these very, very large V scatters. Some things that are, upwards of 1,000 kilometers per second. I wouldn't get too excited about those because those are likely flukes with the pipeline, but there are definitely some weird things that have shown up in the apogee pipeline.
Sometimes it's worth following up those
weird things.
Maybe it's not flukes in the pipeline.
Yeah.
Okay. All right. Thanks a lot.
Oh, excuse me.
Sorry. All right. Your mic.
Yep.
Very good. Your mic. All right. Our next speaker is Jack Hewitt from Goddard, NASA Space Flight Center, and Jack will tell us about the gamma ray view of the sky, I suppose, which is something we actually did not. So it's really the era of gamma ray astronomy right now. I guess I'm getting into your talk right now.
Leave me something. Yeah.
But this is very exciting stuff.
Okay. Yeah, thank you very much, Oleg. It's a pleasure to be here, and I was great when Oleg asked me to give this talk, and I was like, well, how about this topic? And then I realized I only had 25 minutes. But I'll try to be hitting some of the highlights. This is a huge, these are actually two subfields of astronomy, gamma ray astronomy and cosmic ray astrophysics, astroparticle physics. But they're intimately related, of course. Gamma rays being produced by these energetic relativistic particles, and cosmic rays being one of those delightful misnomers in astronomy. They're not actually radiation. They're particles that at relativistic energies that we actually detect here on Earth, or now with Voyager out in space. So so I'll give you some highlights of really interesting questions relevant to our galaxy. And I don't know if anyone's talking on this topic tomorrow for the extragalactic, but there's many other questions outside our galaxy. So to start off as some motivation, the reason we have these subfields of astronomy is because the galaxy and really the universe is filled with relativistic particles. And of course, why is that? And it's because, fortunately for us, space is very tenuous, and so it's very easy to have shocks that obtain supersonic speeds, or just to have bulk motions that can obtain supersonic speeds and cause shocks. And in the case where the density of the medium is very low, we can have what's called collisionless shocks. And this happens all the time, from everything from the solar wind to galaxy clusters. And we see this for a range of different phenomena within our galaxy. So in this particular kind of shock, this collisionless shock, the particle interactions are no longer particle-particle interactions. It's really mediated by the magnetic field. And so we have these elastic magnetic field collisions, and this the shock heating that occurs can essentially be maintained out of equilibrium by accelerating particles, thermal particles, to relativistic energies. So in fact, these collisionless shocks were never observed until we were actually out in space with spacecraft. And that's because for these collisionless shocks to exist, they have to accelerate particles. They have to be in these astrophysical environments. And so we have to have very strong shocks which are actually putting part of their energy into accelerating particles to maintain this entropy difference and conserve energy and momentum across the shock front. And so that's the basic reason why we have particles and collisionless shocks in astronomy and these subfields. But the details are, of course, this was one of the prominent shock acceleration theorists, very obscure. We still haven't sorted these out, and so that's why there's this sort of wealth of science that is yet to be done. And I should point out that these questions have been around for 100 years now. So the impact of the energetic particles that are accelerated by these shocks and that permeate the universe can be seen here. So on the right, this is the cosmic ray spectrum. So this is all of the relativistic particles that are seen locally. And so you can see that the particles are, by and large, dominated by protons with less than 1% contribution from electrons and also some positrons. And in addition to protons, we have all of the different elements being accelerated, and we can measure the abundances of individual elements to find out what the abundances of those original elements are that were accelerated into cosmic rays. But you can see that the spectrum extends more or less as a straight power law up to energies of almost 10 to the 20 electron volts. So these were called the oh my god particles, because they were just such high energies that they were just unthinkable. And we see a cutoff, or the hint of a cutoff here, that could be something related to the GZK effect or something else. But this is all sort of extragalactic origins. What we see, the sort of the characteristic break in the spectrum, the knee, where we go from one power law index to a steeper power law index, is where we think that there's a transition between galactic cosmic rays, so cosmic rays accelerated in our galaxy, and then cosmic rays which have such high energies that they couldn't possibly be accelerated within our galaxy, or we would clearly see them beamed straight at us from the sources. And since we see these basically coming from all directions, they're likely extragalactic in origin. And of course, cosmic rays are interesting in and of themselves, but they have this huge impact throughout astronomy. In tracing shock acceleration and understanding those magnetic processes, and of course as the source of gamma rays, but also as the source of ionization that fuels really all of the deep core chemistry that's very interesting to star and planet formation. They provide the radioactive carbon for dating here on Earth, so they span outside of astrophysics, and they're often used as a catch-all because they are this source. So they've been fingered for global warming, mass extinctions, and the cause of human evolution. So it would be really nice to understand cosmic rays better so that we could prove or disprove some of these impacts that they have.
Jack,
Yeah.
can I ask a quick question?
Yeah.
When I taught I teach high energy astrophysics course here, and I was showing that picture, and someone asked me, like, why do we have so much of the protons compared to the electrons in the cosmic rays? Is there a quick answer to this?
No. Well, it's actually, there's not really a quick answer. In principle, we come up with a quick answer, but it's a nonlinear shock acceleration process. So we could imagine shocks that preferentially accelerate electrons or preferentially accelerate protons. And it appears that the shocks that provide most of the cosmic rays preferentially accelerate protons. Of course, for direct detection experiments, the protons are the particles that can cross the galaxy without losing their energy. Electrons are so lightweight that they quickly radiate away their energy. So you have, you can dump a lot of energy into protons and keep them energetic, whereas electrons will quickly radiate away. I mean, that's, yeah, you could explain that. But in principle, we could have, shocks that only accelerated electrons and have those throughout the galaxy and have more electrons. And as Oleg mentioned, we're really in sort of this, I don't know what to call it, okay, yeah, a golden age of gamma ray and cosmic ray astrophysics, right? We have some great experiments that are currently operating. In gamma rays, we have the Fermi Gamma Ray Space Telescope, which I work on at NASA, and there's many ground-based gamma ray observatories. And we also have direct detection experiments, some of which are satellites, but some of which operate quite nicely in high-altitude balloons. And then there's some really great experiments that have a lot of participation locally. So some of you may have heard of these. Things like HAWK, which is a very high-energy gamma ray observatory. AMS, which is a particle detector on the International Space Station. And IceCube, which is this revolutionary new observatory for neutrino astrophysics. And then it's also, it's also promising for your future careers, if any of you choose to go into these, because there are billion-dollar observatories that have already been approved and are being constructed. So for example, CTA is going to be the next generation gamma ray observatory, which will have an order of magnitude better spatial resolution and sensitivity. And this Gamma 400 mission between the Russians and the Italians should be a very nice extension into both direct detection experiments such as AMS and gamma ray detection, such as Fermilab. So it's a field that is promising now and looks even better in the future. And so what are the key questions that we're interested in? Well, we have a lot of old questions, like the origin of galactic cosmic rays. And I'll call this an old question. Detecting dark matter has long been something of a quest in these energies. But we also still don't know the origin for the cosmic ray electrons and also their antiparticles, which we observe. And then, of course, this last galactic cosmic ray abundances and anisotropy is tied into the origin for galactic cosmic rays. But some of the new measurements that are coming online now are raising really interesting questions about whether we can come up and explain the origin of galactic cosmic rays with simple models. So then we have completely new and unexpected questions. We have these features called the Fermi bubbles, which were not expected at all. We have transient galactic gamma ray sources, which were also not really expected. And perhaps we'll even have some galactic neutrino sources. So the questions I'm going to focus on are just these 3 or 4. The supernova remnant origin for galactic cosmic rays, which is an idea that's been kicked around for about 50 years. Whether or not we can detect or have detected dark matter. And then a bit about these very new, surprising discoveries. All right, so the idea for the origin of cosmic rays that I would say is now sort of not interesting to anyone, but has been around for 50 years, is this supernova remnant paradigm. So the idea was first put forth basically on an energetic argument. We have this much power in cosmic rays observed in the galaxy. We know the resonance time. And we can actually provide that power if we take, say, 10% of the supernova energy and know the supernova rate in the galaxy. And so just based on energetics, not any physics, we can come up with this basic simple argument. So what's interesting is actually figuring out the physics. How does this shock acceleration process work? And does it actually occur? And so this is your basic schematic for shock acceleration. You have some supernova explosion, the blast wave expanding out into space, and the cosmic ray, some poor thermal particle that happened to get accelerated and picked up into the shock and now accelerated to relativistic energies. And this basic shock acceleration mechanism has been around since the late 70s, where they came up with a method that describes, based on the compression that you would see at the shock, gamma, sigma, you should get a compression ratio of 4, and that should produce a power law distribution of particles with index negative gamma. So the index of the power law should be roughly 2. This doesn't agree with what's observed for cosmic rays, but if you account for the escape and their diffusion through the galaxy, it is about what's expected for our cosmic ray sources. So the theory is there. Can we actually observe this? So probably the best evidence we had before gamma ray astronomy for particle acceleration in supernova remnants was through X-rays. We see these very thin synchrotron filaments at the edge of the shock front in very different supernova remnants. And this is, of course, with Chandra, so we have very high spatial resolution. And these very thin synchrotron rims give us clear evidence that the cosmic ray electrons are accelerated to TeV energies and then radiate and lose their energies right at the shock front. So we have very strong magnetic fields and we have very high energy particles. But what we don't have are those cosmic ray protons. So you can imagine some shock acceleration mechanism here producing power law distributions for protons and electrons. And if we look at the energy the radiation that these particles produce, you'll see the synchrotron emission, which peaks in the X-rays. You'll see also inverse Compton emission, the upscattering of, say, the cosmic microwave background by these electrons. And you'll see Bremsstrahlung, the electrons interacting with dense matter. And the only emission process in gamma rays that the protons produce is this pion decay bond. So when the protons interact with some diffuse gas, they'll produce some neutral pions that will quickly decay into 2 gamma rays. And that's how we can actually see evidence for cosmic ray protons at their sources. And the characteristic feature of this pion spectrum is a cutoff at low energies So below the proton rest mass, you essentially have no gamma rays produced. And so we can look for this characteristic pion emission in gamma rays, and if we detect it, then we can identify the efficiency of the cosmic ray sources. So that's finally been done in the last year for the two brightest supernova remnants that are observed in the galaxy. So this is W44 and IC443, and these are two relatively nearby supernova remnants, both about 10,000 years old. So these are explosions that have been accelerating particles for a long time and are actually interacting. You can see it here. There's radio, and then there's some dust emission around the remnant. And these are nearby H2 regions that trace actually a molecular cloud that engulfs the remnant. So you can think of this, if the supernova remnant is the particle accelerator, the target is this dense cloud forming stars that actually surrounds the supernova remnant. So that is producing the gamma rays. And we can actually very nicely see a clear dip at low energies right where we expect to see the pion decay bump. And this cannot be explained so far by electrons. So here we see this very characteristic pion decay spectrum. So if we turn that into a proton spectrum, what we find is that we actually see broken power law proton spectra in these supernova remnants. And so the power law break is shown here. If we convert from photon gamma radiation to the actual proton spectrum here, the break occurs at a few tens of GeV. This is nowhere near what we expect for the sources of cosmic rays, where we expect a break at the knee, PeV energies. So we're about 4 or 5 orders of magnitude below explaining cosmic rays with supernova remnants. But the cosmic ray efficiency is close, 1 to 4%. So this could explain those low energy cosmic rays. And this is uncertain, mostly because of the volume of the target that we don't know. So great, we've disproven supernova remnants as the origin for galactic cosmic rays, right? Not totally, because these are old supernova remnants. So the idea is that we see this supernova remnant, but it could be that those high energy protons have already escaped from the system. And so we actually see some evidence for that here. If you remove the supernova remnant, there's 2 excess gamma ray signals outside the supernova remnant, which are coincident with molecular clouds. And so if you look at their spectra, it's actually coincident or consistent with the idea that pion decay is produced from escaping cosmic rays that are passing through these nearby clouds. And it actually, if we work out the energetics here in this escaping scenario, 3 times as much energy is in escaping cosmic rays as it is still residing within the supernova remnant. So this actually works out quite nicely for explaining supernova remnants as the origin for cosmic rays, if this is what we're seeing. So what we really want is the young accelerators, where the cosmic rays haven't escaped. And so the best one that we have is the supernova remnant Tycho. And you can see very nicely the thin synchrotron X-ray shell, and it's filled with very hot shock-heated ejecta. And so this supernova remnant is actually a type 1a evolving into a very low-density environment. So the gamma ray signal is greatly reduced. So you can see here, this is the SED, the synchrotron spectrum, and now the gamma ray spectrum. And it can be fit with a pion decay model, but it also can be fit with an inverse Compton or a Bremsstrahlung model. So we don't have the statistics at low energies to see this characteristic pion bump yet. But it's hoped that by the end of the 10-year expected mission of Fermi, we might be able to actually have the statistics to see this bump. Of course, the other piece is observing Tycho at very high energies. So hopefully Hawk will detect Tycho at 10 to 100 TeV and prove that this power law extends up to higher energies. And it actually can explain the cosmic rays that we see in the galaxy. But what Fermi can still do in gamma rays is look at the picture in aggregate. Because if we see one supernova remnant accelerating PeV cosmic rays, that would be fantastic. But that doesn't give us proof that all cosmic rays originate from supernova remnants. And so what you can see here is all of the supernova remnants detected in gamma rays so far. And we see sort of an evolution where there's an increase in gamma ray luminosity for the older remnants. And these young remnants are very very faint. So you can, this diameter squared sort of gives you an estimate of the age with time. And it turns out we can look at their spectra. So here are the two pion decay remnants where we nicely see the pion bump. And then this is Tycho, and this is another young remnant in between. So what we see is that the break in energy seems to evolve with time as we go from sort of young, the highest energy accelerators, to old, the lowest energy accelerators. And the density of the target increases. So the cloud wouldn't be reached until very late in the evolution of the supernova remnant, because the massive star, the winds from the massive star would have already cleared out the immediate vicinity. So you're going to evolve into a lower density. So this is the picture that we're starting to piece together, and hopefully with a few more years of data, we can really put the nail in the coffin on this one. And that would give us the energetics of the accelerator, and it would give us, hopefully, the electron-to-proton ratio for supernova remnants. And that could really inform a lot of the theory that we have for shock acceleration in these systems. So that would be great. But, of course, the supernova remnants aren't the only gamma ray source. In fact, they're a very minor gamma ray source. And one of the most interesting sources of gamma rays discovered is the galactic center. So the center of our galaxy, the inner roughly 300 parsecs, is this, you can see here in dust emission, is this very active region for star formation. There's an incredible reservoir of dense gas, much of it forming stars, although very inefficiently. And then there's a very supermassive black hole. It's about 4 million solar masses that lies at the center. What's interesting in particular about this supermassive black hole is that it seems to be dormant. Like probably most supermassive black holes in the universe, it's not producing a quasar or some incredibly bright jet. We see no direct evidence for activity at the moment. And yet, we see evidence for a very bright GeV source. So this region could be responsible for, say, the gamma rays that are seen. And of course, the alternative to that is dark matter. If you look at simulations of large-scale structure formation, this is essentially what we would expect the dark matter halo in our galaxy to look like. There would be a very bright concentration of dark matter right at the center of our galaxy. And if dark matter was annihilating into gamma rays, it would produce a very bright gamma ray signal right there. So you really have a supermassive black hole and some activity, or dark matter. So there's some really great science if we can figure out what this GeV excess at the galactic center is. Sorry. Maybe we can edit that out. All right, so this is the gamma ray sky. And you can see, if we want to explain this, we have to take this data and break it into a collection of sources, galactic diffuse emission from all of the cosmic ray interactions with the galaxy, and then some isotropic emission. And if we do this, we take the data and we try to explain it with known sources of gamma rays. What we're going to be left with is maybe some dark matter contribution or some unknown source. And so when this was first done, about 3 years ago, this is what was found. So these are called the Fermi bubbles or the Fermi lobes. And they were completely unexpected. Sorry, I'll let you read this. So these are residuals. You can see they're highly significant residuals that are seen at greater than 10 GeV. And they were actually first detected and published by a grad student at Harvard. So this is something you could do. So these were found, and they extend roughly 10 kiloparsecs from the galactic center out into the plane, or sorry, out into the halo. So if you turned these and pointed them at us, they would actually reach out to our place in the galaxy. So these are incredibly large structures and very hard spectrum in gamma rays, much harder than the cosmic rays we see, actually. So what is, what is the origin of these? So there may be some counterparts at other wavelengths in the microwaves or in the X-rays, and it's speculated that there, outflows from the center of the galaxy. So what the source of that outflow is isn't clear, and it's also not clear if these are electrons or protons producing the gamma rays. But I think one prominent theory that tries to explain all the observations is that these are cosmic ray electrons that have been, again, accelerated in the outflow. And they're actually tracing not only the outflow source, but they're also tracing a decreasing magnetic field with increasing scale height. So what you see is the faint microwave emission sort of fade out as you go to higher